Greetings to all respected dignitaries, distinguished guests, staff members, my dear colleagues, and participants from various parts of the world. Welcome to 3 days International Online Faculty Development Program on Advancements in Applied Chemistry, AAC 2020, organized by Department of Science, St. Joseph's College of Engineering, Chennai, India. I would like to take this opportunity to thank our most respected chairman, Dr. B. Babu Manogaran sir, St. Joseph's Group of Institutions. Managing Director, Mrs. S. Jessipriya Madam. Director, Mr. B. Sasisegar sir. Principal, Dr. Vati Sesagri Rao sir. Dean, Dr. Parvadavardhani Madam. And Head of the Department of Science and Convener of the program, Dr. V. N. Nandini Devi Madam, for providing us with untiring guidance and needful support for the conducting this program. Applied chemistry covers a variety of chemical fields and various materials, including metal compounds, inorganic and organic compounds, polymers, nanomaterials, and biomolecules. It involves the application of the principles and theories of chemistry to answer a specific question or solve a real-world problem. Nanoporous materials are greater interest both for scientific research and technological applications. Their unique structural characteristics and surface properties contribute significantly for numerous innovative technological applications in chemical production, green chemistry initiatives, photovoltaic devices, and energy storage conversion systems. They provide us more flexible space for reconstruction in fabrication process. As their nanosites expands, the limits and results fact enhanced mechanical stability and large surface area, they opted for photocatalytic activities. In this juncture,
Hello. I think there is some problem. Hello. Hello. I'm not hearing the.
We are working on it, sir. Anand, sir, we are working on it.
No, I'm not hearing the voice of KJ.
Yeah, we are working on it, sir. Wait a minute. Thank you.
Dr. S. Anandakumar is currently a part of Professor Dr. Paulo Miranda's group of Sao Paulo, Brazil. From 2015 to 2019, he was a postdoctoral researcher in the group of Professor Dr. Mauro Berotti at the University of Sao Paulo, Brazil. A research study in the group of Professor Dr. Guy Dinolton at the University of Southampton, UK in the year of 2017. He received his PhD in the year of 2015 from Bharathasan University under the supervision of Professor J. Madhyarasu, Senior Principal Scientist, CSIR. He has published 27 articles in well-reputed journals such as Electroanalytical Chemistry, Electrochemistry Communication, Electrochemical Acta, Sensor and Actuators, Microchemical Journal, International Journal of Hydrogen Energy, analyst, physical chemistry and chemical physics, analytical methods, RNC advances, etc. In his research credential, which have been cited more than 415 times. Furthermore, he was also a reviewer in the aforementioned journals. His present research interests include electroanalytical chemistry, electrochemical sensor, electrocatalysis, and electrochemical energy conversion based on porous nanostructure material for energy, environment, and healthcare application. I would like to conclude this address by encouraging the attendees of this FDP to participate with an increasing number in all the discussion and interaction through this digital platform for next 3 days. With this brief introduction, I hand over the mic to our invited speaker. Dear participants, please join in the providing a hearty welcome to our invited speaker of this online FDP session. Thank you.
Thank you very much for the nice introduction and the invitation to show some of our recent research work in this faculty development program. So before going to start the presentation, I would like to show some of my some information about the university where I'm currently working, and also some funding availability. Let us call the fellowship opportunities for students as well as the faculties. I think it can be useful for this faculty development program. So, the University of Sao Paulo is started at 1934, in the year of 1934, in the state of Sao Paulo. So, Sao Paulo is the biggest city in Brazil, where currently 11 campuses are there in Brazil. Among 4 of them are situated in Sao Paulo, and Sao Paulo have 2 campuses, and the rest of the campuses are in these cities. Almost more than 1 lakh students, which includes undergraduates, masters, PhDs, and postdocs, were studied in this university in different courses. Say, for example, natural sciences, biological sciences, health sciences, humanities, arts, engineering, communications, and social sciences. Apart from this, more than 6,000 professors and 15,000 administrative staffs were currently working in these universities. So this is the library, a well-equipped library, which have all journals and books are available, which is this is close to the Department of Chemistry. Like this, several libraries are there in each department. So for instance, physics department have separate library, biological science have separate libraries. So like that, the university is very, very big university. So there are several libraries are available in each institute. So this is the hospital. The university have the well-equipped hospital facilities, and it's free for all the students and staffs. They also have the excellent sports center and the restaurants. So this restaurant belongs to chemistry department. Like that, each institute have the separate restaurant, and they are providing the very low amount of money from the students and staff. Apart from this, they also provide the bus facilities for each department, as well as each campuses is completely free. So these are all the facilities provided for students in this university. Then, in Brazil, generally there are 2 major funding agencies funded all the projects for professors in Brazil. So this is one of them, called PEPESP, which means the Sao Paulo Research Foundation is one of the government funding agencies supporting the educational fellowships for students from undergraduates to postdoctoral level. So for foreign researchers, so we have two possibilities to getting this fellowship. One is for a postdoctoral fellowship. This is suitable for students who are currently who are recently complete their PhD with less than 7 years. And this is the visiting researcher award is suitable for the faculty members who are willing to visit the Brazil countries if you are working in some universities or colleges and so on. So the postdoctoral fellowship, for getting the postdoctoral fellowship, there are two possibilities that are there. One is the postdoctoral program linked to the thematic projects. So which means here the professors have already the funded projects. So they make an advertisement in this link. If you see here, fellowship opportunities in Sao Paulo. So if you click this link, you can see all the current opening. So the professor, you can directly apply to the approach to the professor, and they will select the students for getting this fellowship program. The other possibility is on-demand postdoctoral fellowship. So where you have to find the host institution in the state of Sao Paulo and then make the proposal jointly. Then you have to submit the proposal individually to the FEPSP. So the FEPSP is evaluating your proposal, and then they will take a decision whether it is approved or not. So this is the another possibility. So usually the FEPSP take initially awarded 2 years postdoctoral fellowship, which is extendable up to 4 years. Generally, they will the FEPSP is taking 100 days for the maximum period to for this evaluation of process, because they send the proposal to 2 reviewers to get the opinion about the novelty of the proposal. Then, based on that, they will decide. They will have a separate committee for the final selection process in the FEPSP office. So they will meet together for a monthly once or twice to finalize the evaluation projects. Then the fellowship stipend is they offered right now it's 7,373 reais, which is equal to $2,000. Of course, now the situation is a little bit not stable. The economic of the Brazil is not stable, so this money is little bit vary. However, once it is back to the normal stage, you will get surely more than $2,000. Apart from this, they will also give 15% of annual scholarship as a contingency. So which is also in Indian rupees around 3 lakhs per annum. So you can use that money for buying chemicals, or if you want to attend a conferences in national as well as the international conferences, you can use that money. There is no problem. Then in addition to this, they also provide a air ticket, to and fro air ticket is completely free for the postdoctoral fellowship awardee. Not only the candidate, they also provide the air ticket for the entire family. If you like to bring your family and child, your wife and child, they also provide the air ticket for them also. So that's really good. Apart from this, they also give 1 month additional fellowship. That means in the first year, instead of 12 months fellowship, you are getting 13-month fellowship, because that 1 month additional fellowship you can use as an installation purposes. So, for example, if you are coming in Brazil, then you need to buy you rent an apartment, or you need to buy your household things. So for that purposes, you can use that money for that money. Then for applying this fellowship, there is no deadline. So you can apply at any time of the year. So you can apply at any time of the year. So this is the criteria for applying the postdoctoral fellowship. So only one major criteria is you should complete your PhD less than 7 years. That is the only criteria. Otherwise, everything is okay. Then, so if you are a faculty, so you can apply a visiting researcher award to the FEPSP. So you have FEPSP is maximum awarded this fellowship from 2 weeks to at a maximum of 12 months. So it is not extendable. And the money is, the fellowship money is different. There is slight differences based on if you are an assistant professor or if you are an associate professor, or if you are a full professor, the fellowship money is a little bit varying. So but the most important thing is here the FSP is supporting the students from the undergraduate level. That is most important. So the the university, the undergraduate students itself, they are participating in their research. That's a really interesting thing. Then this is the website, the SAGI FSP website. Here you have to open your account for submitting your proposal. So normally this website has two languages. One is in Portuguese, it's an official language in Brazil. And then if you click this one, you can see the English version. So where you can open your account and then you can submit your proposal with the required documents. And also you can keep on, they will keep on update the progress of the evaluation process. So it's very simple. Then the another funding agency is called CNPq, which means the Brazilian National Council for Scientific and Technological Development. So this is like our Department of Science and Technology. So this is a national fellowship. So FSP is only supporting the projects at the state of Sao Paulo, not the other cities. But CNPq is the whole Brazil cities. So for getting CNPq fellowship is really tough, because the competition is very high. So the international researchers also can apply, and all the states of Brazil also can compete. So really getting this fellowship is really tough. But the fellowship amount is also a little bit less compared to the FSP. So if you're interested to apply a postdoctoral fellowship, I would recommend FSP is a good option than the CNPq. However, if you are applying visiting researchers, the money wise and both FSP and CNPq is more or less same. So you can choose anyone. So if you are interested, you can apply your proposal by clicking this one. Here also there are two languages, Portuguese as well as in English. So if you open your account here, and you can submit the process. So these two is the major government funding agencies supporting the students for their higher studies. I hope this information can be useful for the students who are students and faculties who are watching the presentation. Okay, well, let me go to the presentation. So the outline of my presentation includes a brief introduction about the porous nanostructures. Especially, I'm going to talk about more on nanoporous gold because I worked for the last few years on that material. So I'm going to talk about more on especially nanoporous gold electrodes. And then where I'm going to talk about the advantages, why we are using the nanoporous gold structures for electrochemical applications, and what are all the issues, current issues on those areas. So based on the current issues, we are deciding the objectives. And then here, this part, the fabrication and characterization of nanoporous gold. So I'm going to talk about much on in this section. Then how we are using the nanoporous gold materials for electrochemical application, such as electrochemical sensor, electrocatalysis, and electrochemical energy conversion processes. And finally, I'm going to summarize the presentation with some future perspectives. So nanoporous gold. So recently, nanoporous gold is widely used for electrochemical applications because it has larger electrochemical surface area and roughness factor. It is a good electrically conducting materials, and more importantly, this type of materials enhance the electron transfer reactions takes place at the electrolyte interfaces, and also this type of material shows very high stability. So these are the major silent features of properties for an electrochemical application. So that's why this nanoporous gold based materials are recently getting more popular in electrochemistry. And generally, this type of materials are prepared in three methods. One is called a de-alloying method. Another one is anodization chemical reduction method, and the another one is the template-based method. So these three methods are mostly used for ferroporous gold fabrication processes. Where in the case of de-alloying method, so this is the AUAG bimetallic alloy sheet. So if you use this type of bimetallic alloy, gold and silver, or in the case of gold and tin alloys, if you immerse this alloy into the highly concentrated nitric acid solution, what happened? The silver ion is selectively removed from the sheet, and you will get such a nice nanoporous structure. It is also interesting to note that the silver AUAG bimetallic alloy is a white color. But after removing the silver ion, you can see the color of the plate is completely changed into brown. So this change of the color indicates the formation of the nanoporous gold structure. So this is widely used because this is the very simple and it is easy for the large scale production. That's why the de-alloying method is mostly used for the fabrication of nanoporous gold structure. And the second one is called anodization chemical reduction method, where the gold electrode is oxidized anodically by applying a positive potential, higher positive potential. For instance, if it's 2 volt or 3 volt or 4 volt, so if you apply a high positive potential to the gold electrodes, then what happened? The surface of the gold electrode is become AU oxides. So this AU oxide is further reduced to nanoporous gold by using ascorbic acid as a reducing agent, because ascorbic acid is one of the very good reducing agent, and also the AU oxides are highly reactive. So when you immerse the AU oxide electrode into the ascorbic acid solution, you will get the high surface area nanoporous gold structure. This is another method. And then here this is called template method, where the anodic aluminum oxide is used as a template to get the well-ordered high surface area nanoporous gold structure. So these three is currently used for this fabrication process. So as I told you in the earlier, this type of materials have very high electrochemical surface area, roughness factor. So here, this is the examples to understand how this type of materials shows the high surface area and roughness factor. So this is the cyclic voltammetric responses of bare gold, that means a flat gold electrode, and this is the nanoporous gold electrode. So where you can see a clear oxide, these three is the AU oxide peaks, and this is the corresponding AU oxide reduction peak. So the high surface area and roughness factor is calculated based on the reduction peak. So if you calculate the area of the electrode, then from that area you can there are some equations, so you can calculate the how much the electroactive area. So compared to the bare gold, nanoporous gold is showing very enhanced current density. So it means that the nanoporous gold shows a high electrochemical surface area. So roughness factor is nothing but the ratio between the electrochemical active surface area divided by the geometrical surface area. So once if you know the electrochemical active area and the geometric area, you can easily calculate the roughness factor. So what is electrocatalytic activity? So if your material shows a very good electrocatalytic activity, means it has two properties. One is, this is an example to explain the electrocatalytic activity to understand much better. So this is the cyclic automogram recorded for oxygen reduction reaction for bare gold, the red color, and then this is the nanoporous gold from the green color, where you can see this is called onset potential. Where the current is raised, this is called onset potential. So the onset potential for bare gold compared to nanoporous gold, it shifted around 300 millivolt towards the less positive, less negative direction. Also, see the peak potential for a bare gold, the oxygen reduction reaction takes place at around minus 0.3 volt, whereas for nanoporous gold, it shows around close to 0. So the potential is shifted towards the less positive direction, as well as the current is increasing. So this, if the material shows this kind of property, then it have the better electrocatalytic activity. Then there is a question, why? How the potential is shifted? So if the materials have large defective sites, say for example, say this material can have large defective sites. So if you have this type of defective sites, it shows some low indexed crystal plane. So this is low indexed crystal plane and large surface defect is enhancing the electrochemical reactions faster and faster. So that's why the peak potential is shifted towards the less negative side. And how the current is increasing, because compared to the bare gold, the nanoporous gold shows very high electrochemical surface area. So the area is responsible for increasing the higher current signal, and the surface defects are responsible for shifting the potential. So these two properties is mainly responsible for the better electrocatalytic activity. Of course, as I told you, these type of materials is also having high stability. So even though this kind of materials have these major advantages, the preparation methods have some disadvantages. In the case of de-alloying method, the high concentration of nitric acid is very much essential. Without this, it is very difficult. You cannot prepare the nanoporous gold structure. And in this case, the anodization chemical reduction method, the chemical reducing agent ascorbic acid is essential. So without this, it is very difficult to prepare the structure. And in the case of template method, the removal of the template requires more complicated processes. So these are all the disadvantages of using this method. Then the question, the idea is arising in our mind, whether it is possible to prepare such a nanoporous gold structures without using any binary alloy or highly concentrated nitric acid, or without using the ascorbic acid. Can you use or can you find any other reducing agent similar to reduce the AU oxide to AU? Or is there any other template method? It's easy without using this kind of anodic aluminum oxide to removal high repeated washing processes. But in order to avoid that, is there any other simple template methods? So based on these questions, we have frame our objective into three parts. So where we prepare the nanoporous gold using anodization electrochemical reduction method. Here we are preparing such a structure without using the chemical reducing agent, binary alloy, and the template. And then we also prepare the nanoporous gold using dynamic hydrogen bubble template, where the electrochemically generated hydrogen bubble act as a template, which is very simple. I'm going to explain in the later slides. And then we find the anodization chemical reduction method. Instead of using ascorbic acid, we have find some other reducing agent which also shows similar properties like ascorbic acid, and then we used for this type of applications. Okay, coming to the first section, the electrochemical sensor. So in this work, we have prepared the nanoporous gold using some unusual electrochemical approaches. By using a single cyclic automogram, we prepare the nanoporous gold structure. So this is the experimental setup where the gold electrode is used as a working electrode, and the silver chloride is used as a reference electrode, and platinum is used as a counter electrode, and 0.5 molar sulfuric acid is used as an electrolytic solution. So in cyclic voltammetry, and if you are using a macro electrode, always you need a 3 electrode setup, because the principles of cyclic voltammetry is if you apply a potential between the working electrode and the reference electrode, then the generated current can be measured between the working electrode and the counter electrode. So if you are using the big electrode like this 3 millimeter electrode, you need always a 3 electrode setup. However, suppose if you are using the micro electrode or nano electrode, the electrode size is, in the case of micro electrode, is 10 micron. In the case of nano electrode is 100 nanometer, 200 nanometer. In that cases, the counter electrode is no need, because if you're using a big electrode, the generator current is very, very high. It's milliampere or microampere or ampere. So we need to measure the current signal between working and counter electrode. However, in the case of microelectrode and nanoelectrode, the generator current is very, very small, nanoampere or picoampere. So that will not change the potential of the reference electrode. So in that situation, we used only a 2 electrode setup. Okay. Well, here you can see this is the cyclic phototomogram of gold electrode in this experimental setup. We are varying the potential from 0 volt to 2.0 volt. So this is this arrow indicate the forward scan, and this arrow indicate the backward scan. So after the forward scan, we hold the potential at this 2.0 volt for different times. Say for example, 10 minutes or 20 minutes or 30 minutes or even 60 minutes. So what happened during the forward scan, the AU electrode, initially it was in yellow color. Then after the anodization process, the color of the electrode is changing from yellow to orange color. So this orange color indicates the formation of AU oxide on the surface of the gold electrode. Then after the anodization, we continue the cyclic phototomogram. Then the formation of the AU oxide is reduced in the reverse scan. So during this reverse scan, the AU oxide is completely reduced to nanoporous gold electrode. See, by recording a single cyclic phototomogram, we can able to get the nanoporous gold structure. In this process, we did not use this bimetallic alloy. We did not use any template. We did not use any reducing agent. So this is a very simple process we proposed for the fabrication of nanoporous gold, just by changing the electrochemical approach. So this is the corresponding cyclic photometric responses of nanoporous gold prepared at a different anodization time, where you can see the reduction current is increased based on the increasing time. So by changing the anodization time, one can able to prepare the different sizes of the different pore sizes of the nanoporous gold structure. So this is the field emission scanning electrochemical microscopic images of the nanoporous gold prepared and corresponding histogram. So where you can see the pore size, the average pore size is around 30 to 50 nanometer using this method. Then, after the fabrication process, we have used this material for continuous monitoring of the dissolved oxygen. So this is I explained in the previous slides. So this is the cyclic photometric responses of bare gold and nanoporous gold for oxygen reduction reaction, where the fabricated material shows excellent electrocatalytic activity for oxygen reduction reaction, and this is the cyclic photometric responses of oxygen recorded at different concentrations from 0% to 71.8%, where you can see the current is linearly increased with respect to concentration. So from this calibration plot, we can calculate the minimum detection limit, and so the other analytical parameters we can calculate from the slope. And this is a nice experiment. In order to show the practical application of these materials, we have performed the experiment. This is called amperometric experiment, where we monitor the current response with respect to time by applying a constant potential of here. This is the reduction potential of oxygen reduction around 0 volt. So we monitor the current with respect to time at an applied potential of 0 volt. So where you can see initially the current signal is 0. So when you pass the oxygen gas into the solution, this is recorded in potassium nitrate, so neutral solution. So when you pass the oxygen gas into the potassium nitrate solution, see the current signal is increases, which means the oxygen concentration increases in the electrolytic solution. Then suppose if you pass the argon gas is removing the oxygen from the solution, which means when you pass the argon gas into the electrolytic solution, the current signal is decreasing, which means the oxygen concentration is decreased in the solution. So likewise, so whenever you pass the oxygen gas, the current response increases. Whenever you pass the argon gas, the current response decreases. So this experiment clearly shows that the fabricated nanoporous gold is a suitable material for continuous monitoring of oxygen sensor. So this is one of the example for electrochemical sensor. Then here, in order to extend the application of the electrochemical application, here we have developed the sensor for hydrogen peroxide monitoring. So this is the scanning electrochemical microscopic images, scanning electron microscopic images of the fabricated nanoporous gold at 30 minutes anodization time. And this is the cyclic voltammetric responses of hydrogen peroxide reduction for bare gold and the nanoporous gold. And this black line is in absence of hydrogen peroxide, and this is the presence of hydrogen peroxide. So where also you can see there is a clear shift in the peak potential. So for fair gold, the red line, the reduction hydrogen peroxide reduction takes place at minus 0.6 volt. However, for nanoporous gold electrode, the same process takes place at minus 0.2 volt. So almost around 400 millivolt, which is very high, shifted towards less negative potential, as well as the current signal increases. With this result shows the nanoporous gold is also suitable for hydrogen peroxide reduction. So this is the amperometric responses of hydrogen peroxide reduction at an applied potential of minus 0.2 volt from 0.01 millimole. That means 10 micromolar to 1 millimolar. So whenever you add the hydrogen peroxide, the current signal is keep on increasing. And then if you plot the current signal with respect to addition of hydrogen peroxide concentration, you can get the linear behavior. So from this slope of the curve, one can able to calculate the limit of detection as well as the sensitivity of the electrode. So if you develop a sensor, the selectivity and stability is also an important analytical parameters. So in order to evaluate the selectivity of these nanoporous gold electrode for hydrogen peroxide sensor, we have performed the experiments, the same like amperometric experiment, in presence of excess of mostly the 10 times excess concentration of the hydrogen peroxide. For that, we have chosen ascorbic acid, dopamine, uric acid, glucose as an interfering molecule for hydrogen peroxide detection. Here you can see the current signal is increased whenever you add hydrogen peroxide. If I add hydrogen peroxide, the current signal is increased. Here, the current signal is increased. However, if I add the ascorbic acid, dopamine, uric acid, glucose, the current signal is not increased. Then later on, if you add again the hydrogen peroxide, the current signal is increased. So this data clearly shows that one can able to use this nanoporous gold as a sensor for selectively detect the hydrogen peroxide even in presence of other substances. Then this is the stability measurements. We evaluate the stability of the electrode also. So when you adding the hydrogen peroxide, the current signal increases. Then you can leave the experiment for up to 20 minutes, even more. This is here. I can give just one example of 20 minutes, where you can see the current signal is stable, which clearly indicate the fabricated material is highly stable. And then, in order to use the practical application, we have collected the mouthwash sample. This is the Colgate mouthwash, normal as usual mouthwash sample from the supermarket. There are two types of mouthwash sample is available. Sample A is without hydrogen peroxide mouthwash sample. Then sample B is with hydrogen peroxide. So initially we take the without hydrogen peroxide mouthwash sample. Then you can see there is no signal. I mean, it shows some current signal, but this is not due to hydrogen peroxide. This is due to probably an oxygen reduction, because oxygen is also reduced at this same potential. So all the experiments are performed in the laboratory experiments are performed after removing the oxygen. But here, this is the real sample. So here we did not remove the oxygen, just we directly used the mouthwash sample from the bottle. That's why there are some oxygen is there in the sample. So this is current is probably due to the oxygen reduction. Then if you add the hydrogen peroxide sample containing O2 sample, then the current signal suddenly increases. Then we have a doubt whether this increased current is due to hydrogen peroxide, or maybe the combination of both oxygen reduction and hydrogen peroxide reduction. That is a question. So how we have to prove this increased current signal is due to hydrogen peroxide? In order to prove that, we have add the catalase and enzyme. This is an enzyme which is selectively consume the hydrogen peroxide from the solution. So we added the catalase into the solution. Then we noticed a decreased current signal initially, and then it takes some time to reach the original background, like the oxygen reduction current. So with this data clearly confirm the increased current signal is due to hydrogen peroxide, because the catalase is consuming only hydrogen peroxide, not the oxygen. So this experiment clearly shows that the measured current is due to hydrogen peroxide. Of course, even though the sensor is highly suitable for hydrogen peroxide, there is a difficulty in presence of oxygen. It will interfere the hydrogen peroxide reduction. So for this sensor, we must remove the oxygen interference. In presence of oxygen, you cannot use this nanoporous gold as a suitable sensor for hydrogen peroxide reduction. So then we think, well, how we have to overcome this issue. So of course, if you study the hydrogen peroxide reduction in the cathodic side, this is the problem. Then we think that why don't you try the hydrogen peroxide oxidation in anodic side? That means instead of hydrogen peroxide reduction, we tried hydrogen peroxide oxidation, because oxygen is not able to reduce oxidize. Oxygen is always reduced. It will not oxidize. So if you, but hydrogen peroxide can be oxidized as well as reduced. So if you study the hydrogen peroxide oxidation, then we can easily overcome the oxygen interference process. So that's why then we started the experiment for hydrogen peroxide oxidation reactions. So where we have prepared the nanoporous gold at the different anodization potential, 5 minutes, 15 minutes, 30 minutes, and so on. We prepare the oxidation, we prepare the nanoporous gold at different times. Then we used for hydrogen peroxide sensor, oxidation sensor. So where you can see, this is the hydrogen peroxide oxidation takes place for nanoporous gold at plus 0.6 volt. However, the red line is the hydrogen peroxide oxidation at bare gold electrode. So here also there is a clear shift in the peak potential, and the current at minus 0.6 volt, there is no current signal, but in the case of nanoporous gold, there is a clear current signal. So this shows the nanoporous gold is also suitable for hydrogen peroxide oxidation. So this is the cyclic photometric responses for hydrogen peroxide oxidation at different anodization time. So when you increase the anodization time, the electrochemical surface area is also increases. That's why the current signal is also increases. So this is the corresponding amperometric responses. We performed the experiment from 10 micromolar to 1.8 millimole, where the hydrogen peroxide oxidation current signal increases linearly with the addition of hydrogen peroxide concentration. So using this slope of the value, we can be able to calculate what is the minimum reduction limit of the hydrogen peroxide sensor. This work we recently published in Journal of Electrochemical Society, I think 2 weeks ago. Then, so far we have prepared the nanoporous gold on a macro electrode, that is this kind of big electrode. The electrode radius is around 3 millimeter size. This is the big electrode. So far we have prepared the nanoporous gold in the big electrode, and then we are thinking, why don't you try this kind of the same procedure for the micro electrode, because micro electrodes generally have many advantages compared to the macro electrode, because macro electrode shows very low double layer charging current, then it enhance the mass transports very high compared to the macro electrode, and they have very low IR. So these are all the advantages of micro electrodes, and also you can easily use for practical applications, especially for biomedical applications. microelectrode and nanoelectrodes are widely useful. So in consideration of this application, we have fabricated the microelectrode in our laboratory, where this is the gold wire, 25 micrometer size of gold wire. We inserted, this is the pasteur pipette, it's very cheap. So we inserted this gold wire, this is 2 centimeter gold wire. We inserted here in the pasteur pipette, 1 centimeter inside and 1 centimeter in outside. Then we used the aral tape for shielding the gold wire. Then we use we fill with carbon powder. After sealing the process, we use vulcan carbon powder to take the contact. So this is a nickel chromium wire for the contact purposes. Then after this preparation is very simple. We just use the gold wire, aral tape, and then carbon powder and then nickel chromium wires. There is no instrument here used. Just by hand we can prepare this type of microelectrode in the laboratory. So after the sealing process, we can polish the electrode until to get the gold gold surfaces. So once the electrode is ready, so we use this electrode as a sensor, nanoporous gold microelectrode as a sensor for arsenic detection for environmental application. Because arsenic is also one of the heavy metal ion, which is highly toxic in drinking water or the sea waters. According to WHO Health Organization, the allowed organic concentration in the drinking water is, I think, 10 ppb, 10 parts per billion. If it is exceed the limit, then it is become very dangerous. So for that, we need a sensor for arsenic. So after the fabrication of the microelectrode, we use the same procedure, anodization followed by electrochemical reduction method. Then we prepare such a nanoporous gold structure. So this is the scanning electron microscopic images of bare gold microelectrode. See the size. The size is around, the radius is around 12 micrometer size, very small size. So where also this method is applicable to prepare the nanoporous gold electrode, and then we used this as an arsenic sensor. Here you can see this is the bare gold microelectrode for arsenic sensor, and then this is the nanoporous gold electrode. So for that we use square wave anodic stripping voltammetric method. It's nothing but it's a stripping analysis. Generally, for this type of heavy metal detection, stripping analysis is widely used. So stripping analysis is nothing but stripping. It contains two-step process. One is pre-concentration step, another one is the stripping step. So pre-concentration is nothing but the very small amount of metal ion present in the solution first reduced and deposited at the surface. This is the pre-concentration step. Then the deposited metal is stripped away from the electrode surface, where you can get this kind of voltammetric signal. So this is the principles of stripping voltammetry, generally used for this technique for heavy metal detection. So this is the square wave anodic stripping voltammogram recorded for the arsenic sensor, starting from 2 parts per billion. ppb means parts per billion to 30 parts per billion. So the current response is clearly increased with respect to the concentration. So from this slope, we can calculate the limit of reduction and other analytical parameters, of course. So in order to evaluate the interference, when you detect the arsenic, copper is one of the major interference, because normally copper is also stripping peak is also appear at the same potential. So that is one of the major problem. When you're without modification, you will get even though if you have arsenic and copper, you will get a single peak. However, in presence of nanoporous gold microelectrode, there is a clear separation of copper and arsenic. It's almost around 300 milliwatt differences, which is more than enough for analytical purposes. So where we perform the experiment, we keep the copper concentration constant, and then we increase the arsenic concentration. See, the current signal is clearly increased without changing the linearly increased. However, if you see, there is a current drop for the copper stripping peak. This is because copper maybe form an alloy with the nanoporous gold. That's why it's slightly affected. And then we demonstrated for the real sample using the tap water by using standard addition method, where also we get the very good electrochemical stripping behavior. So this research indicates the nanoporous gold microelectrode is also suitable for arsenic sensor for environmental application. Then in the same way, we prepare the nanoporous gold microelectrode and use for a dopamine sensor for biosensor application. So this is the microelectrode. This is another way of preparing the microelectrode. This is still very, very small microelectrode in the size of around 5 to 10 micrometer. I think the radius is around 5 to 10 micrometer, which is very, very small, and we cannot see the surface by eye. We have used microscope for preparing this kind of electrodes in the laboratories. Then we use the similar procedure to prepare the nanoporous gold. So this is the cyclic automatic responses of the barcode and nanoporous gold microelectrodes, where you can see the similar trend as is shown in the previous slide. And this is the electrode we prepared. This is the micro. This is the small tip of the microelectrode we taken from the scanning electron microscopic images. This is the without modification and then with modification. There is a clear difference on with and without modification of nanoporous gold microelectrode. This is the dopamine oxidation, cyclic automatic responses of dopamine oxidation recorded in phosphine buffer solution. So where you can see there is a clear change. This is the red line is the barcode electrode, and this is the nanoporous electrode. So there is a clear difference in the shift in the oxidation potential as well as the increased current signal, which indicates the excellent electrocatalytic activity of the nanoporous gold for dopamine sensor. And this is the square wave automatic responses to record the calibration curve. From this, we can, this sensor, the developed sensor, shows the minimum reduction limit of 30 nanomolar. So the idea of using the microelectrode instead of macroelectrode is to get the high sensitivity. When you use the microelectrode, you can achieve a micromolar level or sometimes nanomolar level. But if you use the microelectrode, you can easily achieve the low reduction limit in nanomolar level, or in some cases even picomolar level concentration is also possible to detect using the microelectrode. That is one of the major advantages of microelectrode. Then this is another way. So far we prepare the nanoporous gold for the first method, anodization electrochemical reduction method. And then now I'm going to explain the new method, so-called DHPT method, which means dynamic hydrogen bubble template method for preparing such a macroporous structure. So where the experimental setup is the same, where this is the gold electrode, and then we use the reference electrode for silver chloride, and platinum is the counter electrode. If you apply my very high cathodic potential to the gold electrode, say for example is a -4 volt per 100 seconds we apply, then what happened in this high negative potential, the hydrogen bubbles are coming out from the gold electrode surface, and then the metal ions, the gold precursor was also there in the electrolytic solution, and this potential, the gold ions are diffused and then deposited over the gold electrode surface. So both process takes place simultaneously. So the hydrogen bubbles are coming out from the electrode surface at one direction, and then the gold present in the solution go and deposit on the nanoporous on the gold surfaces. So this hydrogen bubble can act as a template to form this kind of a porous structure. So once if you remove the electrode, then the template is immediately removed. This is very simple. Instead of using the anodic aluminum oxide as a template, that requires many processes to remove the template. But here, the electrochemically generated hydrogen bubble act as a template, which is very simple to remove the process, also getting this similar structure. So this way, this is also another simple way you can prepare the high surface area nanoporous gold structures. Then this also we evaluate for hydrogen peroxide sensor, where also we get the excellent electrocatalytic activity for hydrogen peroxide detection, and this is the corresponding amperometric responses from 20 micromolar to 0.36 millimole to 0.36 millimole concentration range. it shows a linear increment in current signal. And this is the stability measurements, where we studied the stability of the electrode in two ways. Here you can see the continuously cycling the electrode for 100 cycle. So even that the gold oxide reduction current is not decreased much, which clearly indicates the fabricated electrode is highly stable. And then this is hydrogen peroxide. When you add hydrogen peroxide, the current signal is increased. Then we leave it for under 1000 seconds. Then the current signal is almost stable. So this data, this cell shows the hydrogen peroxide is highly stable for this nanoporous gold surfaces. And this is another example of electrochemical sensor for nanoporous gold prepared in DSPT method for nitride. Because nitride is also one of the important analyte to monitor, because most of the foodstuffs have the nitrate content. So if it is extend the level of, I think, according to environmental, I think the food agency, the maximum allowed concentration of nitrate in foodstuff is around 900 or 90 ppm. So if it is exceed, what happened? The nitrate can oxidize the iron present in the hemoglobin to Fe2 plus to Fe3, that is ferrous to ferric in the hemoglobin. Then the entire body of the blood circulation will be affected. So that's why the nitrate sensor is also an important is also an very, very important. So then we have tested the nanoporous gold for nitrate oxidation. Here you can see this is the black line is for bare gold electrode, and the nanoporous gold is the green line. So where also we get a clear shift in the oxidation potential as well as increased current signal. So this is the amperometric responses for nitrate detection. We started from 1 micromolar to 1000 micromolar, very long linear range. So whenever we add the nitrate, the electrode is responded well and the current signal is increases. So if you plot the current versus the addition of nitrate concentration, it shows a very high linearity. So from using this method, we can achieve the limit of reduction of 10 nanomolar, which is very, very low compared to the normal level. So one can able to use this material as a sensor for nitrate. Okay, see, this is another way. So far I explained in two methods for the fabrication of nanoporous gold. One is for anodization electrochemical reduction. Another one is called anodization dynamic hydrogen power template method. And this is another method. This is this experiment is we done based on some curiosity, because so this is the gold electrode. We anodize 15 seconds and you will get in AU oxide. After that, in electrochemistry, the dopamine and ascorbic acid will oxidate at the same potential. That is one of the big challenge to separate the oxidation of ascorbic acid and dopamine. So when the literature, based on that, we think that why don't you use dopamine instead of ascorbic acid? So just one day we just tried this experiment, and we very much surprised. The AU oxide, when I immerse the AU oxide electrode in the dopamine solution, immediately, instantaneously, the color of the electrode is changing from orange color to the black color. So which indicates the formation of the nanoporous gold structure. So this is the corresponding scanning electron microscopic images of the nanoporous gold and polydopamine functionalized nanoporous gold. Actually, initially we did not know whether the polydopamine is present on the nanoporous gold. After taking the SCCAM images, we understand, okay, there is also polydopamine as present in the solution, in the surfaces, because AU oxide is highly reactive. Then it will oxidize the dopamine into polydopamine. Polydopamine is one of the good characteristic adhesion behavior, so that it adherent on the electrode surface. So which is confirmed by cyclic automatic responses. So this is the cyclic automatic responses of polydopamine recorded in phosphate buffer solution without any dopamine analyte. So this clearly confirmed the dopamine was present in the electrode surface. So then we used for as a sensor for hydrogen peroxide, This is the cyclic automatic response of gold, nanoporous gold, and then polydopamine functionase nanoporous gold. So it shows an excellent electrocatalytic activity, and this is the corresponding ampermetric responses. We also used this for the dopamine sensor, where also we will get the nice electrochemical behavior as well as the analytical parameters. Then, coming to the second section is electrocatalysis. So I think I have enough time. I will go a little bit fast, and we have a few more slides only. So coming to the second application of electrocatalysis, this is an interesting paper we published recently, where we prepared a platinum decorated nanoporous gold for methanol oxidation reactions. So usually for platinum and nanoporous gold, where people are using two-step method, where they first prepare the nanoporous gold and then deposit in the first step. The second step, they deposited PT on the nanoporous gold. But however, in this work, we prepare the PT nanoporous gold in a single step. See, the gold electrode is cycled from minus 0.2 volt to plus 0.2 volt. After the forward scan, we simply hold the potential as usual, and then we reverse the AU oxide is reduced during the reverse scan. And here, after the AU reduction, we inject the platinum precursor into the solution in order to reduce the PT over the nanoporous gold. Here, the idea is why we have to add the PT after the nanoporous gold. Because if we add here, say for example, if we add here, you will get AU PT alike, not PT decorated nanoporous gold. That's why we add the PT precursor after the nanoporous gold in order to get the PT decorated nanoporous gold structure. So this is the corresponding PT region of the fabricated electrode, where we can see the clear PT oxidation, PT reduction, and then the hydrogen desorption and hydrogen absorption peaks. So this hydrogen desorption or hydrogen absorption peak is only possible when you have a PT. You cannot get this kind of behavior for gold electrode. So this is clearly indicate that the PT was present on the nanoporous gold structure, and this is the corresponding the scanning electrochemical microscope, scanning electron microscopic images of nanoporous gold and PT decorated nanoporous gold electrode, where there is no much difference between two, because PT, but however the energy dispersion EDX analysis shows there was 2% of PT was present on the surface. But why it's not showing any differences between these images? Because PT was atomically, when very thin layer of PT was deposited on the nanoporous gold. That's why there is no clear much difference on the SEM image, but it have the PT. The cyclic autometry is clearly proved PT was present on the nanoporous gold. Then we use this material as a catalyst for methanol oxidation reaction, where this is the black, this is the bare gold, and this is the nanoporous gold, and this is the bare PT electrode, and this is the PT decorated nanoporous gold electrode. So compared to these three electrodes, the PT decorated nanoporous gold electrode shows an excellent electrocatalytic behavior for methanol oxidation reaction. And using this electrochemical surface area, we calculated the specific activity of the methanol oxidation reactions, where it shows around 40 milliampere per centimeter square specific activity, which is very high compared to the existing PT nanoporous gold based electrode. Also, one of the interesting thing, the electrode fouling, because during the methanol oxidation, carbon monoxide is formed as a byproduct, which absorb on the PT surface and inhibit the performance of the catalyst. That is one of the big problem in methanol oxidation reaction. However, in this case, the PT, the generated cobalt carbon monoxide is not inhibiting the PT surfaces, because this experiments was performed on potassium hydroxide solution. So the hydroxide ions absorb and chemisorb on the nanoporous gold surfaces, and then which further oxidize the formation of the carbon monoxide, and thereby inhibit the fouling of the carbon monoxide on the PT surfaces. Because nanoporous gold is also a good catalyst for carbon monoxide oxidation reaction. So this is the interesting research we published recently in Electrochemical Communication Journal. And then this is another example of the nanoporous gold application for oxygen reduction reaction. So where also we have seen excellent electrocatalytic activity for oxygen reduction reaction. This is the bare gold electrode, and this is the classic carbon electrode. So bare, usually oxygen reduction takes place in two pathways, either 2+2 reduction or direct 4-electron reduction. If you have a very good catalyst, then you will get the direct 4-electron reduction, that is oxygen to water. If you have a poor electrocatalytic activity catalyst, then the 2+2 electron takes place where the oxygen is reduced to hydrogen peroxide, then hydrogen peroxide is further reduced to oxygen, water. So our catalyst is a very good catalyst. So the direct 4-electron reduction takes place. That means the oxygen is directly reduced to water. So how we confirm the direct 4-electron reduction takes place? So in order to confirm that, we perform the RDE experiments. From this, we use the KL plot. From the KL plot, we calculated the number of electrons, so which is around 4. So which clearly is confirmed the fabricated nanoporous gold islands is a good catalyst for direct reduction of oxygen to water. So coming to the last sections, so this is the electrochemical energy conversion reaction applications. So this the same material was used for electrochemical energy conversion applications. For that, we have chosen hydrogen evolution reaction is an example for this applications. So here you can see this is the polarization curve, linear photometric polarization curve recorded for classic carbon electrode, gold electrode, PT, and then nanoporous gold islands. So where the fabricated nanoporous gold island shows a similar behavior like PT. Because PT is one of the very good catalysts for electrocatalysis. So, but because of the high cost, the people are trying to replace the PT or to use the low content PT. So that is the advantages. So if you use a nanoporous gold, it's almost shows like a platinum behavior. And this is the corresponding Tafel plot. We can calculate from this Tafel plot, we can define the mechanism. What kind of mechanism takes place at the electrolytic interfaces. So these are the stability studies for 1000 cycle and 2000 cycle. So this is the previous cycle, and then after 1000 and 2000 cycle is also indicate a similar behavior. And this is the amperometric performance for recording the durability of the catalyst. So even up to 20 hours, it shows a similar current signal. So this research indicates the nanoporous gold island is also suitable for hydrogen evolution reactions. So this is then the final example for hydrogen evolution reactions. So we also tested the nanoporous gold prepared by anodization electrochemical reduction method, and that also shows a similar platinum-like behavior for hydrogen evolution reactions. So we are currently working on that. So in summary, actually we have prepared the nanoporous, the high surface area nanoporous gold in different ways. Say for example, anodization electrochemical reduction method, dynamic hydrogen bubble template method, or the anodization followed by chemical reduction method using dopamine as a reducing agent and used as an electrochemical sensor for dissolved oxygen, hydrogen peroxide, dopamine, arsenic, and nitride for electrochemical sensor application. And then we used as an electrocatalyst for oxygen reduction reaction and methanol oxidation reaction. And the hydrogen evolution reaction is also we have studied for electrochemical energy application. So far we have mostly studied the use of the nanoporous gold for different electrochemical applications. Now we are interested to functionalize the nanoporous gold, say for example using conducting polymers or other metallic nanostructures for palladium, cobalt, nickel, and copper. And suppose if we can also modify using some mediator for biosensor applications, and you can also use some enzymes for glucose sensor. Can also possible to modify the L-cysteine for some electrochemical applications. So we are right now we are working for surface functionalization of nanoporous gold for different applications. So at last, I would like to thank Professor Mauro, because all the work was done with Professor Mauro. and I would like to thank all my colleagues who are all involving the works. They are the postdocs, and these are the PhD students, and then these are undergraduate students. So I would like to thank each and everyone for contributing their for the fruitful collaboration. And this is Professor Paulo. I am currently working with this professor. And finally, I would like to thank the PEPSP and CNPQ for financial support for last 5 years. And I also would like to thank the University of Sao Paulo for giving all the facilities to carry out these studies. And then I would like to thank the chairman, managing director, principal, dean, and the convener, also the program coordinator, for all program coordinators for St. Joseph College of Engineering for giving me such a great platform to share some of our research work in this faculty program. Finally, I would like to thank all the students and faculties who are watching this presentation in the live stream. Thank you, Anandal, for your kind attention.
Thank you, sir. Thank you very much for your interaction, research, as well as guidance to postdoctoral research. Now, the questions from the audience will be posted in your screen. You can answer one by one, sir.
Okay. I think I will take 10 minutes more. Sorry.
No problem, sir. No problem, sir. Hope the session will be useful for all the delegates. Nearly more than 400 participants have participated and watching lively, sir.
Okay. Thank you very much.
Dr. Subhash, you can pose the question one by one.
Yes.
Thank you, sir.
Sir, this is the first question.
Yeah, I am. So he asked why we are using the platinum metal as the electrode in the standard hydrogen electrode, why we cannot use some other transition metals. So this is platinum is one of the best material because it's a noble material. If you are using some other metals, it's easy to corrode. So if you are using a standard hydrogen electrode is the best reference electrode so far in electrochemistry, and where the hydrogen, because hydrogen absorption is only takes place on PT, it will not takes place on other metals. I think probably it may be possible for palladium, but PT is always best catalyst. That's why still for standard hydrogen electrode, PT is the best metal. So that is the best one. So we cannot replace the PT. So PT is one of the best choice because it's a noble metals and you can use for a long time. Then what is the effect of silver?
Next question.
What is the effect of silver in the original metals of AG that is needed to be de-alloyed? Can we also have alloyed nanoporous material? Okay, so if you see the bimetallic alloy is essential to prepare the nanoporous gold using de-alloying method, because silver is like a sacrificial method. You can use silver or tin, which type of materials easily removed from the surface when you immerse in the highly concentrated nitric acid solution. That's why the bimetallic alloy is needed to prepare the nanoporous gold structure using de-alloying method. Suppose if you have only gold electrode, you can also deposit the silver by electrochemical method on the gold electrode surface. Then you remove this silver by electrochemically, where also you can get this similar structure. So it is possible. Yes. In this, then another, he is asking a very good question, because in this de-alloying process, even though if you remove the silver from the AUAG alloy, there are some residues still present on the gold electrode. So using the disadvantage of the de-alloying method is we cannot able to remove completely 100% silver when you immerse in the nitric acid solution. That is one of the disadvantages using the DLI method. However, if you are using our method, so-called anodization electrochemical reduction method, you will get 100% purity of nanoporous gold electrode. That is the difference between the DLI method and the our method.
Okay, sir. Next question.
Will the electrochemical oxidation process is used for treat the wastewater? Yes, of course, there are many reports are there. You can use the electrochemical oxidation process for wastewater treatment. You can use it. There are many reports are there. You can, the electrochemistry, the idea is the electrochemistry is not only for chemistry. So electrochemistry is an interdisciplinary. You can use for many applications. As an engineer, you can collaborate with the engineers to develop the potential stat. You can make a collaboration with the biochemistry people to develop a biosensor, and you can use you can easily collaborate with material science, because material science, they are preparing various types of nanostructures. So we can easily electrochemistry is completely an interdisciplinary. So anyway, we can work together with the any sciences. So I think it's possible. There are many applications for wastewater treatment. It is possible.
Thank you, sir. Next question.
Yeah, using platinum metal. I think it's the same question. This is the same question.
Okay.
The first question.
Yeah,
Platinum metal.
next question.
Yes, sir. Next question, sir.
Yes. Why only silver chloride is used as a reference electrode in the triple electrode set? Okay. So actually, the silver chloride is a secondary reference electrode, because usually people are using silver chloride or saturated carbon electrode as a reference electrode for because the standard hydrogen electrode is very difficult to maintain the atmosphere, because it's always we have to maintain 1 atmospheric pressure and 25 degrees Celsius. That is very difficult always. But in order to avoid this, some people are using silver chloride or saturated carbon electrode as a secondary reference electrode, which is easy for our convenience. Some of the researchers use this electrode and then they convert the potential to standard hydrogen electrode. So this is the way. So it's easy, it's convenient, and we prepare these. Actually, we are not buying the silver chloride electrode commercially. Actually, we are fabricating the silver chloride electrode in the laboratories, which is very easy. We used, that is a pipette tip. We use a pipette tip, right? We prepare the reference electrode in the pipette tip. We have some membranes, we put this membrane and we have to use the silver wire. We deposit the silver chloride electrochemically. Then you can right away use the silver chloride reference electrode, which is very easy. So for that purpose only, people are always working with the silver chloride for our convenience.
Okay, sir. Thank you, sir. Next question.
Okay, so he is asking where the nanoparticle gas sensing studies are available. So in electrochemically, I think one of my colleagues, Dr. Abhishek, he was working with me in Brazil for last 3 years, and his PhD was gas sensor. And now he is working in France. He was working the nanomaterial, the same material, the nanoporous gold structures for gas sensing application. We also, I think one of the PhD students, his name is Douglas, he was working for nitric oxide, gas nitric oxide sensor. I think there are many reports. You can use that as a nanoparticle for gas sensing applications. So, I don't have much experience on gas sensor, because I think it is possible. I have seen many papers, electrochemical applications particle for gas sensing. It is possible.
Okay, sir. Next question.
Does hydrogen peroxide corrode the electrolyte? No. Hydrogen peroxide generally used for even cleaning purposes. If something is corroded, if you put that electrode in the hydrogen peroxide, it will clean. As hydrogen peroxide is a good solution to cleaning the vessels also, the glass layers used for the laboratory. We use hydrogen peroxide for cleaning purposes, so it will not corrode it. So it is because if for hydrogen electrochemical sensor we use very small quantity, micromolar or nanomolar, sometimes only millimolar. So that is not going to be corrode the electrode surface, because gold, we use gold electrode. Gold is also a noble metal. So and also it's not easy to corrode. That's why we would be platinum, gold, and we used for many applications. You know, hydrogen peroxide is not able to corrode the electrode material. There is no problem. You can use it.
Okay, sir. Thank you, sir. I think it will be a last question.
Yes. Direct and indirect electrochemical oxidation. Okay. So for this is a good question, because there are two possibilities. Either you can measure the electrochemical signal by direct electrochemical oxidation. So far, I showed the data all with direct electrochemical oxidation. I'm not using any mediator or I'm not using any enzyme. So where the indirect electrochemical oxidation is, if say for example, if you are using the glucose, if you want to reduce the glucose, so where we say for example, if you take a nanoporous gold, no problem, nanoporous gold, then you modify the gold on enzyme glucose oxidase. You can use glucose oxidase, then you can use the hydrogen peroxide. It takes place, you can, at the glucose oxidation reaction, there is a hydrogen peroxide oxidation will take place parallelly. Then you can, that signal is proportional to the concentration of glucose. So where the indirect electrochemical reaction takes place, that is one of the example. Or you can use the, I think we did one paper, I remember that the NADH, I think. I don't show here, that is very old paper. So NADH oxidation, where you can use some redox mediator. So normally the indirect method was used for biosensor applications. Some of the biomolecules are not electrochemically active, but you want to measure the electrochemical signal. In that situation, people are using some redox mediator or some potassium ferrous some standard probe as a side reaction. So by measuring that signal, one can able to quantify the electrochemical oxidation of the analyte of your interest. So this is the difference between the direct and indirect electrochemical oxidation. So far, I'm working mostly on the direct electrochemical oxidation process. So the indirect electrochemical oxidation process takes place for biosensor applications. So this is the major difference. Okay.
Yes, sir. Okay, just
Is there any other questions? Or?
KJ, sir, please unmute.
Okay, sir. In the absence of any question, I request Dr. Subhash to conclude day one session.
Thank you, sir. Thank you very much, sir. Nice presentation. Sir?
Yes.
So hear my voice?
Yes, sir, you can proceed. Yeah, you can proceed.
Thank you very much, sir, for your kind presentation. Very good, excellent session, as well as very good answering by the lot of questions from participants. Thank you, sir.
Thank you.
Dear participants, we have posted the feedback link in chat box. After filling the chat box, you can leave. Thank you, sir.
Yeah, thank you very much.
Sir, thank you very much for spending your valuable time with us. Really, the session was useful for us. I hope nearly more than 400 participants have benefited by your lecture. Thank you so much, sir.
Thank you very much for giving these opportunities.
Yeah, it is our pleasure, sir.
Yeah, thank you very much. Thank you all. Thank you, Dr. Subha, and Dr. Suresh, and Dr. Saran, and thank you one and all.
Thank you, sir.
Yes, thank you. So,
dear participants, kindly find the feedback link in the sandbox. By completing the feedback link, you will get the e-certificate. Carefully find the feedback link and fill it.
So is it okay? Can I close?
Yeah. Thank you, sir. Thank you, sir. You can leave now, sir. Thank you very much.
Thank you. Thank you.
சார் யூடியூப் லைவ் ஸ்டாப் பண்ணிடலாமா?
Yeah. Okay, sir. You can stop.
No.
Wait.
Feedback link போட்டு ஸ்டாப் பண்ணுங்க. Feedback link போட்டுட்டு ஸ்டாப் பண்ணுங்க.
ஃபீட்பேக் லிங்க்
சார் ஃபீட்பேக் போட்டுட்டே தான் இருக்கேன் சார், போயிட்டு இருக்கு. இங்க எனக்கு
Yeah,
visible
Okay,
ஆ
wait for 2 to 3 minutes.
அங்க போறோம்.
Wait for 2 to 3 minutes.
One minute sir.
The feedback visible இல்ல சார்.
நான் போயிட்டே தான் இருக்கேன் சார். இப்படி போட்டிருக்கேன், இங்க வருது எனக்கு.
இல்ல அங்க
Sir, வேற யாராவது type பண்ண
இங்க
முடியுமா?
ரிஃப்ளெக்ட் ஆகலையே சார் அந்த chat boxல.
இப்போ 1 minute.
சுபாஷ் சார் நீங்க வச்சிருந்தீங்கன்னா இதுல போடுங்க சார்.
சார் இதுல ஸ்ட்ரீமர்ல சார்.
இந்த இதுலயே போடுங்க. இந்த லைவ் கமெண்ட்ஸ்லயே போட்டுருங்க.
ஓகே சார்.
கேஜே சார் ஒரு இன்ஃபர்மேஷன் அப்படி சொல்லுங்க. ஒரு 2 minutes வெயிட் பண்ண சொல்லுங்க, போட்டுறேன். Thank you.
தான் போட முடியும் லைவ் கமெண்ட்ல.
சார்
சுபாஷ் சார் நீங்க தான ஹோஸ்ட்? ஹோஸ்ட் நீங்க தான சார்? சுபாஷ் சார் நீங்க தான சார் ஹோஸ்ட்?
ஆமா சார்.
நீங்க லைவ் கமெண்ட்ல அந்த ஸ்ட்ரீம் யார்ட்லயே லைவ் கமெண்ட்ல போஸ்ட் பண்ணீங்கன்னா உங்களுக்கு போய்டும்.
ஓகே சார்.
சுரேஷ் சார் நான் இங்க போட்டுட்டு தான் இருக்கேன். மத்த கமெண்ட்ஸ்லாம் போது ஃபீட்பேக் மட்டும் போட்டுறேன்.
அதான் ஃபீட்பேக் தான் சார்.
போட்டுட்டு தான் இருக்கேன். எனக்கு இங்க விசிபிளா தான் இருக்கு.
ஓகே சார்.
இல்ல ஆனா ஃபீட்பேக் லிங்க் போல எல்லாரும் கேக்குறாங்க வேர் இஸ் தி ஃபீட்பேக் லிங்க்னு.
ஓகே நான் போட்டுட்டு தான் இருக்கேன். ஒரு செக் பண்ணிடுறேன் ஒரு நிமிஷம்.
இப்போ சுபாஷ் சார் போட்டது
வந்துருச்சா சார்? எதுல வந்திருக்கு சார்?
சுபாஷ் சார் போட்டாரு அது வந்து அதான் அந்த இதுல கமெண்ட்ல.
ஓகே சார். வந்துருச்சு சார். தேங்க்ஸ் சார்.
சுபாஷ் சார் இன்னும் ஒரு 2-3 தடவை போடுங்க.
ஓகே சார்.
சுபாஷ் சார் இப்போ இது கட் பண்ணிடுங்க. லைவ்
கட் பண்ணி
எண்ட் ஸ்ட்ரீம் கொடுத்துருங்க. எண்ட் ஸ்ட்ரீம் கொடுத்துருங்க.